All right, guys, welcome back. Let's settle down. Get your notes out. Pretend to care. Don't make me yell at you. It would not be a good idea. All right. Artem, come on. All right, we left off yesterday. I had just introduced the idea of what a Lewis base was. Um, so very quickly, just to finish up our definitions from yesterday. A Lewis base is essentially anything with a lone pair. And so anything with a lone pair has the potential to go share that lone pair with a Lewis acid. Remember, Lewis acid is something that can accept a lone pair to make a bond. So can anyone think of what an example of a Lewis base might be? All right. Oxygen. So oxygen in a specific compound. What compound might have oxygen in it? All right. OH minus could be a Lewis base. Sure. It's got lone pairs. How about H2O? That could be a Lewis base. O2. In some circumstances, that does act as a Lewis base, particularly when you breathe in and you get oxygen that binds to hemoglobin. It's binding to an iron ion in your in the hemoglobin molecule. So it's one of those lone pairs that donates. All right, what other element often has a lone pair? Nitrogen, so things like ammonia are good Lewis bases. Really good Lewis base is cyanide. That's what cyanide is. Yep. Or carbon monoxide is another really good one. So essentially, anything that has a lone pair to donate will be a Lewis base. Now, one thing I want to note, when we gave the definition for Lewis acid, it was a little different than Bronsted acids. But we said Lewis acids could then act as Bronsted acids. So a Lewis acid is really kind of a broader definition. It encompasses some acids that the Bronsted definition doesn't. Same thing with Lewis bases. Anything that is a Lewis base could potentially act as a Bronsted base. So anything with a lone pair, like, say, NH3, if it uses that lone pair to go make a bond to H+, then it's acting as a Bronsted base, right? So if this lone pair is used to go bond to H+, then it's acting as a Bronsted base as well. So the Lewis definition can also encompass the other things that we called NH3 a Bronsted base. When it's acting as a Lewis base, though, instead of grabbing H+, it would be going to bond to some lone pair acceptor. So we gave as an example of a Lewis acid BF3, also known as BFFF. This is like the perfect pairing of a Lewis base and a Lewis acid. because the nitrogen's like, I've got a lone pair, and the boron's like, ooh, I want electrons. So these two can come together and make a bond. So that would be an example of a Lewis acid reacting with a Lewis base. And that's pretty much as I'm going to say about the Lewis definition. From this point forward, we're going to kind of ignore Lewis acids and Lewis bases. If we ever want to refer to them again, we will say Lewis acid or Lewis base. But from this point on, if I say the word acid or base, I'm referring specifically back to that Bronsted definition. So to remind ourselves going forward, a Bronsted acid is a H plus donor, a proton donor. And a Bronsted base is something that takes H plus. So a Bronsted base would be an H plus acceptor. And those are the definitions we want to focus on going forward. And then lastly, there's a couple other words you're going to hear. Number one, back in the day, one definition of whether something was a metal or a nonmetal was if you took an oxide of that element and you added it to water, would it make an acid or a base? This was mentioned back in the reaction types lecture. So if you took a metal oxide and added it to water, generally it made a base. If you take a nonmetal oxide like SO3 and you add it to water, it makes what we call an oxyacid. Back when we talked about Lewis structures, we also mentioned these oxyacids. The formula is usually written like H2SO4 or HNO3. So it's got the H out front, and then it's got the whatever other nonmetal element, and then it's got the oxygens. But remember that the structures of these things, the hydrogen is always bonded to the oxygens. So in an oxyacid, the H's are bonded to the oxygens. So H2SO4 has a structure that looks like this. Or HNO3 is the one that throws people off a lot. They want to bond the hydrogen to the nitrogen, but HNO3, the hydrogen is bonded to one of the oxygens, not to the nitrogen. So you take a nonmetal oxide plus water, it makes one of these oxyacids. I throw that in there for historical reasons, not because we're necessarily going to focus on that kind of reaction. But we will see a lot of this kind of acid, H2SO4, HNO3. Remember that the H's are bonded to the oxygen. And I'll come back to those later. And then we have another term that you'll hear sometimes, amphoteric, or amphiprotic. I don't know why it has to have such a complicated name. But these are things that can act as either acids or bases, depending on what's around. So to act as an acid, what do you need to have? Well, but to act as an acid, if you are going to be an acid, what do you need to have as part of yourself? Hydrogen. You need to have H plus that you can possibly give away. If you're going to act as a base, what do you really need to have? Not OH minus. You don't need to have OH minus. By the way. You need to be able to accept H plus. And generally to accept H plus, how do you accept H plus? You have to have a lone pair. All right. So amphiprotic things or amphoteric things have to have a lone pair and they have to have H plus. So most common examples would be one that we see all the time. And I'll go back to our reaction we said we're focused on. In this reaction here, notice one water molecule is taking a proton from the other. So one of them is giving away H+, one of them is taking H+. So that means water is an amphoteric substance. It can act as an acid or a base. So water can act as an acid or a base. It can take H+, if you add an acid to it, it'll make H3O+, or it can lose H+, to make OH-. Some other amphoteric substances we'll see would be some of these ions that have H+. They've lost an H+, but they could also have another one to give away. So another example would be things like HCO3-. HCO3- could take a proton from something to become H2CO3, or it could lose its second proton to become CO3-2-. So those are things we call amphoteric. And then polyprotic, we've given that definition before. Polyprotic acids would be things that have more than one proton to potentially give. So what's an example of a polyprotic acid? H2SO4, H3PO4 is another one. So anything that has multiple H's that it can possibly give away would be a polyprotic acid. Good question. The question is water polyprotic? Water would not be considered polyprotic. And the reason is, yes, you could take away one proton to make OH-. But then one thing you will never, ever, ever see is OH- losing a second proton. Right? That is never, ever going to happen. And so you wouldn't call water polyprotic. So it's not enough for something to have hydrogen in it, but it has to have a hydrogen that can possibly be taken away as H+. And, to figure out when that's possible and when it's not possible is a hard thing to get a feel for. So I'm going to give you an idea of, all right, how can you tell when something's an acid or when something can act as an acid? Because there are lots of things with hydrogen in them that will never act as acids. So for instance, methane gas, CH4, has 4 hydrogens, but it's never going to act as an acid. All right. Are there any questions about the definitions we've given? So let's move on and talk about equilibrium. So for an acid, when an acid dissociates, we can write a general equation for that. An acid is a proton donor. So the chemical equation for an acid, it has to have H. And then if we want to just write a generic acid, we usually call it HA. And we said it can split up into H+. And leave behind the rest of it. And most of the time that's reversible. When is that not a reversible reaction? Good question. When A minus precipitates out. Yeah, there are cases where you have that A minus precipitate out, and that would kind of pull this equilibrium to the right. So that's a good point. Not the one I was thinking of, but if you added something that could precipitate with A minus, whatever this ion is, by Le Chatelier's principle, that could pull it to the right, like we saw with the cobalt. We could pull the reaction in one direction by adding something that precipitates. But I'm thinking of a more something you were asked to memorize earlier in the year that you still need to know. When does this reaction not go back and forth, but only go in one direction? When you have a strong acid, all right? When you have a strong acid, this would be a one-way arrow because it happens 100% and doesn't go back. But for most acids, for weak acids, this will be in equilibrium. So my dissociation equation looks like this, and then we call the equilibrium constant for that reaction Ka. All right, we're back following technical difficulties. All right, if I'm going to write the equilibrium expression for this reaction, what's going to go in the numerator, what's going to go in the denominator? Products of reactants. So that would be H plus times A minus over concentration of HA. So for example, why don't you write the Ka expression for acetic acid? So specifically for acetic acid, the numerator would be H plus. And then the thing that's left behind after an acid loses H plus is called that acid's conjugate base. So A minus here is the conjugate base. So for, in the case of acetic acid, what would the formula for the conjugate base be? All right. And then in the denominator, I would just have acetic acid. All right. So that's our general Ka equilibrium expression. Anytime you're given a Ka value, and when it's time to start doing problems, I'm actually going to give you a copy of a Ka list out of the book. So you'll have a bunch of Ka values at your disposal. You should be able to set up the equilibrium expression that goes with it. Okay. For polyprotic acids, you're going to see multiple Ka values. So for example, H3PO4, if you look it up, you'll see 3 Kas listed. You'll see Ka1, Ka2, and Ka3. Why do you think there are 3 Ka values? It can lose 3. So there are going to be 3 equilibria that we look at. H3PO4 can lose its first proton, and that leaves behind H2PO4 minus. So the equilibrium constant for that reaction is going to be Ka1. What do you think the reaction that Ka2 corresponds to? That might be, it might be logical to say for it losing 2 hydrogens, but it's actually not for it to lose 2 hydrogens. for it to lose the second one. So in other words, for Ka2, the equilibrium is going to start with H2PO4 minus. That can lose H plus and leave HPO4 2 minus. So that would be the equilibrium that goes with Ka2, and then Ka3 would be for it to lose the third proton. So, any idea, is it going to become easier to lose protons after you've lost one, or is it going to get harder? In other words, do you think Ka1 is bigger than Ka2 and Ka2 is bigger than Ka3? Or do you think Ka1 would be the smallest and then Ka2 would be bigger and then Ka3 would be bigger? All right. So it will get harder because you have electrostatic attraction between H plus and the ion, right? After you've already removed one proton, you have a negative ion. If you're a proton, you're much more attracted to that than you were before. So it's going to be harder to remove a proton once it's already negative, and then it's going to be even harder to remove the third proton. So in general, Ka's will always get smaller as you go. All right, so let me define Kb before we reach the end here. For a base, what is our definition of a base? What do bases do? They accept H plus. So for a base, we're just going to call it B. That doesn't stand for boron, it just stands for a generic base. That's going to react with water. That's going to make OH minus. And then this thing we call BH plus, which will... What name do you think we give that? This is the conjugate acid of the base. Because remember, if you are a base and you grab a proton, now you have a proton that you could potentially give away. So now you've become an acid. So these things we call conjugate pairs. HA and A minus, they're a conjugate pair. An acid and its conjugate base. B and BH plus, they're a conjugate pair, a base and then its conjugate acid. Because if you're a base, once you gain a proton, now you become an acid. If you're an acid, once you lose a proton, now you become a base. So our general form for Kb, what's going to go in the numerator? OH minus times BH plus. And in the denominator, just concentration of B. Why not H2O? It's a pure liquid. All right. So that's our Kb expression. So for ammonia, NH3, what's the Kb expression going to look like? All right, concentration of OH minus times NH4 plus over concentration of NH3. So we're going to use Ka and Kb so much. So you want to be able to look at any acid and write its Ka equilibrium expression just off the bat. Same thing with a Kb for any base. You want to be able to write its equilibrium expression right away. All right, so that's a skill you're going to practice. Unfortunately, that's where we're going to have to call it for today. We'll get into acid and base strength next time.